Now here I am talking about angular SHM on horizontal rough surface. Angular SHM on rough surface. Okay, so let us take one example, and just in order to keep this question easy, I am taking a case of solid cylinder. Right, so the question is like this. Suppose that there is a solid cylinder which is of, let's say, mass m. It is connected with a spring which is massless, okay, and spring constant or stiffness is k, okay, and here this surface is rough, and assume enough friction is available. Suppose that, like, what I'm trying to ask in this question, that calculate the value of time period of small oscillations made by the cylinder without slipping on the horizontal surface. This is a pretty advanced level question. So basically, rotation plus SHM is involved, right? Because here I said that there is no slipping, means this is the case of pure rolling. So here we have actually two ways to solve this question. One is our traditional way of rotation, so that we can apply that way, and we can find out the answer. And another way is regarding angular SHM we can apply. So let us do both methods. So first method, so in first method what I am saying, suppose that if I draw the situation, of course for the SHM what I used to do, I will try to compress or extend. So let's say I compressed this spring with some distance x. So let's say now this is sphere reaches to this point, and this is x compressed, right? If that is true, then if you see this sphere at center of mass, because if you see the FBD of this spring, this will try to restore, so it will have some kx force, right? So if you see, sphere will have some kx force like this, and because I said that bottommost point there is no slipping, right, on the horizontal floor, so this point will have no slipping. That means in order to provide that no slipping, because if there is the force, then of course I can understand there will be a torque about this point. Because of this kx, you can see this point will try to go backwards, right? So that means only force is available which is available here, which is friction force. So friction will act like this, and I said that friction is large enough, so we need not to talk about friction enough, because it is large enough. So now if I see the separately FBD of this sphere which I have drawn, I can make this here to analyze this method better, like this was the sphere, okay, and there is one force which is kx, another force is the friction force. Of course I can assume this mass of the acceleration of the center of mass is ACM, and as you can see that because of this friction force, okay, and because of this kx, okay, friction force, there will be certain amount of acceleration generated alpha. So at point P, if you see that acceleration will be ACM outwards or in left direction, and because of this alpha r, acceleration will be alpha r, which is rightwards. So as there is no slipping, we know that, then for that ACM minus alpha r has to be 0, because this touches the ground and ground is not having any acceleration. So we get the condition ACM is equal to alpha r for our calculation part. Now we know that for rotational mechanics we need to have a equation for torque. So this is the point O, so we can write the torque about O. So torque about point O I am writing. So of course this kx will not have any torque because it is just passing this point O itself. So that means this is having 0 torque, and of course this friction force will be having some torque, so F into R, and we know that in rotation this will be ICM into alpha because I am writing about center of mass. So here this will be K, this will be 0 plus F into R, and for the sphere ICM into alpha, sorry, this is cylinder. So for cylinder ICM will be mr square by 2. This is solid cylinder. So mr square by 2. So F into R is equal to mr square by 2 into alpha. R is cancelled out, so we get m by 2 alpha into R. Interestingly, we have alpha R is equal to ACM, so we write m by 2 into ACM. So that's how we get another relation between F and MACM. Now this is not the single task which we have to do. Another task is also there. What is that task? We can also write the equation of dynamics. So this was the equation for rotation motion, and then for dynamics, what is there for dynamics? So we can see kx is the force minus F, so this is the net force because Newton's second law relation says ma into ACM. So we got another equation. Now we can apply this F is equal to m by 2 into ACM. So we can substitute m by 2 into ACM is equal to m ACM. So this will be 3 by 2 m ACM will be is equal to kx, and we can write ACM is equal to 2 by 3 k by m into x. So this is the center of mass acceleration. That means this is the restoring acceleration, right? This acceleration is restoring acceleration. So our acceleration in SHM will be given by minus ACM. That means A is equal to minus of A restoring. So A will be is equal to minus 2 by 3 k by m into x. So now clearly you can see that A is proportional to minus x. That shows this is the SHM, and if this is the SHM, we can compare A is equal to minus omega square s. This is the general equation of SHM of acceleration. So in SHM, if this is true, then minus omega square will be equal to minus 2 by 3 k by m. This is cancelled out. So here we got angular frequency, which is 2k by 3m value of omega, and if that is true, now we can find time period. T is equal to 2 pi by omega. So if you substitute that, 2 pi under root of 3m by 2k, this is going to be the answer. for time period. Okay, now this is one way of doing, and this is complicated one. Now the easier part can be, so now I can tell the easier part of second method, which can give you a little bit fast answer, but that is pretty advanced method. You need to have some basic idea of rotation in that, which is instantaneous, IAOR, instantaneous axis of rotation. So this is moment of inertia about instantaneous axis of rotation. So understand, suppose that if you have a situation where suppose this sphere or any body is performing pure rolling, then we can say V naught is equal to omega naught R, because this point will not have any slipping, right, instantaneously. So we will simply write V naught is forward, omega naught R backward. So V naught minus omega naught R is equal to 0. That means V naught is equal to omega naught R. We know that, right? Now, if that is true, then this point is center of mass. So this is one axis of rotation, but this point, so if that is happening, that if bottommost point is point of pure rolling, then this will be instantaneous axis of rotation for this body. So basically what I want to say, let us suppose that this body is, let's say this, calculate the velocity of this point. So we know that V naught will be the velocity of translational motion, and because of rotation there will be omega R. So you know that this will be 2 V naught, because omega R is equal to V naught here. But if you apply the method of instantaneous axis of rotation, from there you can say this body, instantaneously you can assume this body is rotating about this point. Actually this is not happening, but instantaneously you can assume this. This is the proven method. That's why people apply this method in order to get fast answers. Now this distance is 2r from this point. So if you want to calculate a velocity of this point, let's say a, similarly you can directly write omega into 2r, because you are assuming this is rotating about this point, which is the point, let's say B. So similarly you are getting 2 omega r, and you know that this was V naught and this was omega naught. So similarly you can say this is again 2 V naught. So same answer you are getting in one step. So this is an instantaneous axis of rotation. This is important concept in rotation. So once you know this, now I am removing and coming back to our original question and method 2, because I have to apply this format. That's why I taught you this thing. So second method is, suppose that this was our sphere, okay, and this was our spring. I assumed that this sphere is rotated theta angle. So basically that time I said in SHM, in normal SHM we displace the block with x displacement, but in angular SHM what we do, we displace this block with certain angle theta. You remember the simple pendulum? So we used to dislocate this pendulum like this, displace with certain angular displacement theta. So here theta is the angular displacement. So now if that is true, that means this sphere will rotate like this, and it will try to compress this particular spring. That means suppose if K is the stiffness, then I can say that this distance will be, because this is R, let's say this is S, we know that S is going to be R into theta. So basically this X will be is equal to, or this compression will be, this compression in the spring is going to be simply K into R theta, right? So if this is K into R theta, that means, as, why I'm saying this, because this is connected to this point, right? So this sphere will go like this, so obviously this angle is theta. So understand, this theta is very small, so that's why it is not like that it is so huge, it is just like this. So you can assume this as straight only. That's why I did for X, right? When I was taking X, I said that stiffness or compression is like this, otherwise your compression will not be the same. So if that is true, then you can say that force is K into X. So this time if you draw the FBD of the sphere, so you will see there will be a force which is K into R theta on the sphere. And now of course if this point will have the tendency to rotate, and obviously if this have this force in this direction, obviously this bottommost point will try to slip. So direction is like this, right? For alpha, so for alpha I'm trying to draw. So of course alpha, this is the value of ACM, acceleration. So for that purpose there has to be alpha which is in opposite direction. So obviously friction force in this direction, right? So here friction force is in this direction, and this is going to be K into R into theta. Now if that is true, what I can do here, I can say this point P is going, or B will be the instantaneous axis of rotation, IAOR. And if I use that relation, then I can say torque about IAOR will be IIAOR into alpha, right? Correct. And obviously I can say that torque about this point B, of course this friction force is passing from this point itself, so 0 into perpendicular distance is F plus this kx, so K into R theta. So of course this will be -1 because it is the restoring torque, and into perpendicular distances R. So this is going to be the net torque. And IOR, so of course moment of inertia about this point. So we know that solid spheres moment of inertia about center of mass is mr square by 2. So moment of inertia about IO or IB will be using the parallel axis theorem, which says ICM plus md square. Here ICM is mr square by 2, this is mr square, so this is 3 by 2 mr square. And if you use that, this will be 3 by 2 mr square into alpha. So this is a simple thing, but conceptually this is very important. Conceptually it's a bit tough thing, so if you understand properly, then only you can apply, otherwise you apply your old method. So yeah, if that is true, then I get here, what do I get? This r and r square will be cancelled out, so this alpha is equal to minus of 2 by 3 k by m into theta. And then you know that this is the condition for angular SHM, because alpha is the angular acceleration which is proportional to minus of theta in angular SHM. So this is angular SHM, and if this is angular SHM, we can compare minus omega square into theta. So from here we can compare, so omega is minus omega square is equal to 2 by 3 km, and this minus minus is cancelled out, omega is under root of 2 by 3 km. You are observing that we are achieving the same result which we earlier got. Similarly, t is equal to 2 pi by omega, so t is equal to 2 pi by omega is under root of 2k by 3m, so this is 2 pi under root of 3m by 2k only. This is going to be the answer. So that's how we can solve such type of questions related to Angular SHM. And in fact you can find answers very easily. So many concepts were involved, like Angular SHM, then instantaneous axis of rotation. So rotation itself is involved, rotations concepts were involved. So pretty precious question for all of you, specifically for NEET. Okay, yeah.